talking about Vakyansh, okay? So first of all, how many people know about speech recognition here? Okay, quite a few. So all those people who actually don't know about speech recognition, let me show you something first. Can we play the video if possible?
मैं आज यहाँ पे आपका हार्दिक स्वागत करता हूँ। आज हम वाक्यांश के बारे में बात करेंगे, तो चलिए शुरू करते हैं।
Okay. So a couple of points here. So whatever you're seeing here is everything built in-house. Okay, so from model to the streaming client to model deployment, everything is done in-house. So we are not using any third party. And the best part about this is it's all open source. Okay, so if you want to add a voice capability in your applications, just going home after this talk, you can very well do that. Okay, and there are a lot of other components that are also there. So I'll tell you what happened. Okay, so the input was voice, okay, my voice, okay, and my voice was transcribed in the text there. So there is a model that actually transcribes from voice to text, okay, and then there is a text-to-text model that actually punctuates the text. So if you see that there is a sentence ending at whom, and then we have a sentence ending at the end as well, right? So these are the models that we are building, and we are not just building models, we are also building data for creating these models, okay? And that is what we are going to discuss about next, okay? And if you think that a speech recognition system is only in Hindi at the moment, so it is in 18 languages, okay? So I want to show you a small demo in another language. So let's hope it works.
ਚੰਡੀਗੜ੍ਹ ਪੰਜਾਬ ਅਤੇ ਹਰਿਆਣਾ ਦੀ ਸਾਂਝੀ ਰਾਜਧਾਨੀ ਹੈ।
Okay, so I'm not sure how many people know Punjabi here, but if anybody knows Gurmukhi script, they can very well verify, or I can verify on your behalf that it is correct. Okay, so moving ahead, so this is basically a project, Vakyansh, which is basically speech recognition in Indic languages. So I will be talking about the challenges that we have faced here while creating this project and how did we overcome that challenges. But first of all, I want to actually motivate why do we want to actually work on Indic languages, why it is important to work on Indic languages, right? So I'll give you one statistic, very interesting statistic. So the number of speakers with English as the first language in the world is 373 million, okay? So number of speakers in English as a first language in the world is 373 million. Can you guess how many speakers are there for Hindi as a first language in India? Anyone else? Sorry? 50 crores. That is 500 million, if I'm not wrong, right? Okay. So it seems that you're quite close, okay? So it means that the number of speakers speaking Hindi as a first language in India is far greater than the number of speakers speaking English as a first language in the world, okay? So can you recognize the scale of the people who are speaking this language and the extent of applications that we can develop if these applications are developed in the native language, right? So I talked about Hindi here. What do you think is the second most spoken language in India? Somebody said something from there. Yes, so that is correct. The second most spoken language as a first speaker in India is Bengali with 100 million speakers. And that is also not a very small number at any scale, right? And so that is why if we want all these people to be a part of a digital ecosystem, right? If we want all these people to be part of a digital apps that we are building, it will be more beneficial if we build these apps in native languages so that these people get onboarded quickly and they actually contribute to the digital economy as well, right? So that is why working on Indic language is very important at this point of time, but there are quite challenges in this journey, right? So it's, seems easy to be honest, right? But there are a number of challenges in this journey, right? And the number one challenge that we have is that you do not have open data in any Indic language present currently, okay? As I said, open data, data present in open source, either for creating models or for testing the models, right? And then Hindi with 575 million speakers as a first language is a low resource language as compared to English, which has 373 million speakers as a first language, right? So low resource means that not enough models, data sets exist to actually build better systems in those languages, right? So even Hindi, it's quite a popular language, but it is still low resource in India. And so that is where we introduce Vakyansh. So Vakyansh is basically our try to convert the status of Hindi from low resource and other Indic languages from low resource to high resource. Okay, and we'll talk about the journey, like how this has happened and what were the challenges while building these systems, right? So again, I mean a quick reminder. So what is automatic speech recognition? It's basically giving a machine the ability to understand spoken language or sound. So basically there is a signal and then there is a system that transcribes the text. So once you have the text, you can build NLP system on top of those text to actually understand what is the intent or anything that you want to do. Either in call center analytics or maybe analyzing the sentiment of the caller or anything like that, okay? So as I said, what is Vakyansh? It is basically created as a speech recognition system for Indic language. And when I say system, it means from end to end. That is from data creation to model deployment, okay? So it's not just that we created models, we built data, we created models on that data, and then we pushed those models to production, okay? And the objective of Vakyansh was very clear from the starting, that we need to focus on the 23 Indic languages, first of all, in first phase, and then open source all of these state-of-the-art models or data sets because we want to share our learnings and the resources that we create with the community. Because what we want to do is we want to actually make an open ecosystem, right? So there are some services that exist in the native languages, but that are not open source at the moment. So even if you want to create a system in your native language, you need to pay someone to actually build a system in native language, right? So our objective was we'll open source everything from model data sets so that people can engage with the community and build better apps in the native language, right? So I'll quickly talk about the overall process, right? So what is the data requirement? Because we said that the main challenge here is the data, right? Data creation is one of the biggest challenges. So first of all, what type of data do we require for an ASR system, okay? So let's say if we are building a system for 575 million people, right? So that data has to be representative of the entire population, right? And we need an audio and a text pair in a ASR data pipeline, okay, to create the models, okay? So this is basically the overall process. Our data collection and our data building pipeline is divided into 3 different pipelines. So data collection, validation, processing, and filtering. And then once the data is created, we do some experiments using deep learning models like Web2 and conformal-based models as well, right? So I'll quickly talk about all of these data, our data creation pipeline, okay? So the first step is, in order to get data, what do you do? Okay, so you go to internet, you crawl the internet for the open data present, right? So we created crawlers that actually go to the entire internet to find open source videos that can actually serve as a data input to our pipeline, right? So using crawlers, we wanted to actually automate the process of data collection. Okay, so we do not want to go to YouTube and collect every open video manually. It would take us years to do that, right? So we created a crawler that actually crawls the internet. It gives us an open source data in a particular language in which we are trying to build. And I'll talk about how do we validate this data, okay? So the second part our data creation pipeline was chunking, right? So let's say I go to YouTube, I get a video of 90 minutes. Now this 90 minutes of audio or video is not useful to me because I cannot feed that 90 minutes audio or video to any system due to hardware constraints and other stuff, right? So what I want to do is I want to actually break down the audio into smaller chunks, okay? And now there are multiple ways to actually do this, okay? So one of the ways is that you chunk at regular intervals. You say that every 10 seconds I'm going to chunk my audio. But the main problem with this approach is that at the chunk endings, you have words with that have overlapping boundaries between chunks, right? So some words can get missed in the ending. So a better way to actually do this thing was to do intelligently, that is using voice activity detection, okay? So it detects the silence in the audio, and wherever a silence is noticed, it actually breaks the chunk, okay? And of course, you can configure the amount of silence that is required to break the chunk here, okay? So so once we have chunks, what happens is we have a data validation pipeline. Okay, so because when we are going to entire internet to crawl the data, you may not get the data that you want. Okay, so you need to validate that the data that you are collecting is correct or not. Okay, so the first step was language identification. So suppose I want to build an ASR for Hindi, right? I go to YouTube and crawl the internet. It is not very sure that the videos that you've crawled are in Hindi language only, right? So we created a deep learning classifier, okay, that actually tells us whether it is in Hindi language or not. Now, this itself is a very hard problem to solve, right? Because the not Hindi class is virtually infinite, right? So Hindi we know is a Hindi, but not Hindi can be Tamil, Telugu, English, songs, music, anything, right? So we use a high precision classifier here to actually tell us whether our chunks have the language in Hindi or not, okay? And a little bit of noise can enter into the data set at this point, but that is okay if you're collecting a huge quantity of data, okay? And the second is songs and music identification. So if you have, if you're crawling the internet again, you'll get a bunch of quantity of songs and music, right? And this is not the right data set or ideal data set for an ASR task. So we want to remove these songs or music from our data, right? So we created a deep learning classifier that actually classifies between I mean, whether it is a song music or a vocals, right? Now again, it's a relatively easier problem to solve than language identification, but still a very hard problem to be honest, right? And then we have is removing noisy samples using SNR. So SNR is signal to noise ratio, which actually tells that how much background noise is present in your data, right? So SNR gives you a decibel value, okay? And you can say that anything, so we had a threshold of 20 dB. So anything less than 20 dB was rejected based on the chunks, right? So this is the data validation pipeline. Now, as a data scientist, we want to actually understand how our data looks like and whether our data is representative of the entire population or not. Okay, so basically, as I say, data science is not magic. The magic lies in the data creation step, right? So if you are creating the wrong data, you get the wrong model. So the next step was to actually understand what my data looks like, okay? So for that, we created data processing pipeline. And in the first step of data processing, we identify the speakers in the data set, okay? This is a very important step because what we want here is to actually get a rough estimate of the speakers in the data set. So if I'm building a, let's say, 10,000 hour data set, it should not be the case that my 8,000 hours of data is coming from a single speaker, okay? So the max limit that we put in our data set creation was 30 minutes. So if we are collecting a data set and building a data set for 10,000 arcs, it means we need to collect it over 20,000 different speakers. Then only it will be a representative of the population for what you are building, right? And the second step here was gender identification. Again, I mean a very important step, because if you're building a data set, you don't want that 100% of a data comes from a single gender, right? So let's say, and it also directs you like what you should do in your data collection pipeline. Let's say in Telugu, we had 90% of the data only from female speakers. So we understood that now we have to collect more data from the male speakers, right? So this is why we do a gender identification. Again, we do not, it's just to understand the data. It's not to actually do any other processing using this data. And then, as I said, chunk duration. Due to hardware constraints, we can only allow chunks less than 15 seconds into a pipeline. Okay, and this is because there are I mean, even the best of the AI system or CUDA-based systems, you get out-of-memory exception if you try to train longer, I mean, models with longer input size. And then the last part is transcription. That is a very important part, because what we want is an audio plus text pair, okay? And for transcription, we actually do it in an automated way. We use commercial STTs to transcribe our data. Now here we are not dependent on a single STT. We are actually transcribing our data from multiple speech-to-text engines so that there is no bias. And in a data collection process, I mean, if you use inputs from multiple sources, then and if you have a large enough data, then deep learning is powerful enough to understand what are the errors in different sources of data. Okay, so this was our entire data collection pipeline in brief. And which brings me, and using this data collection pipeline, we were able to process 20,000 hours of data in Hindi. And out of 20,000 hours of that data, 4,000 hours of data was finalized, I mean, passing all the filters that I have talked about. Right? So this was, I mean, first of a kind of trying to build something using the open data that is present on the internet. And we quickly realized that this approach is good, but it may not scale for other languages. Like for a language like Odia, you do not have even enough audio data present on the internet. And you do not even have a commercial STT that is present for Odia to transcribe the audio, right? So at this stage, we actually switched our modeling approach. We went from supervised to semi-supervised learning. And I want to ask you one question here. I mean, do you think if that is technically feasible? So if you want to create a speech recognition system in Hindi, can you do it only using the English data? What do you think? Feasible? No? Well, so the answer is yes. And my colleague Anirudh will talk about how that can happen. And so, Anirudh.
Hello. Hello. Can you hear me? We'll talk about it. We'll show it. Yeah. My mic is audible? Okay. So how can we create speech recognition systems in Hindi using English or any other data? So first we have to think a little more deeply about what languages sounds are, right? So what are accents? So accents are something which we pronounce. And where do we learn our pronunciations? From our mother tongue, right? So let's say I am coming from North India and I'm speaking English. That means that the sounds I learned during my childhood in speaking Hindi, I am just using those sounds to speak English. And that is why all our accents are so different from each other, right? And you can particularly tell from where a particular accent is coming from. It can be South Indian English accent, a Russian English accent, or so on and so forth. What I'm coming to is that there's even a more fundamental unit of sound known as phoneme. So phonemes are basically common between languages also, right? And as my colleague talked about, that supervised learning may not be the perfect approach if you want to scale this approach to make models for different Indic languages, right? Okay. So what does semi-supervised approach do? We trained a model, we call it CLSIR 23, cross-lingual speech representations for Indic languages. So we collected around 10,000 hours of data across 23 Indic languages, and this was the first effort in Indic language space, which was open source at the time. And we basically trained this model so that it could learn cross-lingual phoneme information across languages, so that we can use it for further fine-tuning tasks like speech recognition and so on and so forth. So this is basically an interesting plot which you can see. So once we trained our semi-supervised learning model, and we have these embeddings, and they have learned phonemes for different speeches from different languages, right? And we were just trying to understand how these look like, do they even make sense? So we basically projected them to a lower dimensional space, and then we were looking at them, and you see the clusters. The cluster on the left bottom is Assamese, Bengali, Odia, and these lie in a single cluster. And this makes sense because these languages actually sound the same or similar, right? Similarly, there's a cluster in the middle, which is Urdu, Hindi, Sanskrit, Punjabi, Gujarati, right? So whatever we trained actually made sense because similarly sounding languages or languages with more common phonemes are being clustered together, okay? This is how we basically verified our approach. There's also a paper which we published. You can have a look for more interested audience. So now, once we have this, you have an architecture so that you can use it for further downstream tasks like ASR, right? So initially, if you are using a completely supervised learning approach, the number of hours of audio data used to be around 4,000 to 5,000 hours, at least, if you want to get a SOTA model, okay? But if you are using semi-supervised learning approaches, and these approaches are fairly recent, I mean, a lot of work was going on in these approaches. 2 years back, I think Facebook AI came with the first Wave 2 Vec 2 and similar approaches. And now, if you want to create good models, which are performant, which are accurate, you don't need as much data. The time has reduced from 4,000 to 500 to 100. Even some researchers claim that you can create speech recognition models with 5 minutes of data or 10 minutes of data. That is why my colleague said that you can actually create Hindi models with a lot of English data, maybe just you need some data for supervision. And that is why it is possible in this day and age. This was not possible maybe 2 to 3 years back. So this is the accuracy of our models. These are some of these benchmarks are open source, some are not. And we actually benchmark some of the other commercial engines as well. And you can see that we are almost outperforming everyone in terms of word error rates. And there are some languages which were not seen before in ASR space, like Odia, like Punjabi. There are so many others. There are other low-resource languages as well, which we were able to generate models for. How we created labeled data for them is another story, but using some tricks and intelligent techniques, we were able to gather some data for low-resource languages like Dogri, Maithili. And for these languages, even data didn't exist before. So we have models in all these languages, even Nepali, Bhojpuri, Rajasthani. So yeah, I mean, this is possible now, and using these self-supervised learning approaches, semi-supervised learning approaches, you can create state-of-the-art models with very less amount of data. And this is what we need. So ASR is one part. You have created a lot of models. You have generated a lot of data. With less data, you can train models in different languages. But there are different utilities as well, right? An ASR output by itself is not very useful. If you dictate a 10-minute audio to it, it will just be a blob of text which you might not understand, even the machine cannot understand, right? So we developed a bunch of utilities around it so that the output is more readable to the user. The user experience is enhanced, right? And things like automatic punctuation, inverse text normalization, domain adaptation. I'll talk about each of these. So the first is automatic punctuation. So if you want to understand the task, the output from the ASR model is just the text. You want to punctuate it, basically. So we basically used an Albert encoder. This is another NLP technique. We use subvert tokenization, then pass it through an Albert encoder, and then we have a linear error on top. Basically, we created a lot of label data, with punctuation and text, and we were able to create automatic punctuation models for 12 Indic languages, and which we saw in the demo also, as my colleague pointed out. In Hindi, we had Viram. Even in Punjabi, we had Viram, right? And all this is open source, by the way. You can download our models from a GitHub page, use them in your applications. The second thing I wanted to talk about is inverse text normalization. Now, what is inverse text normalization? So normally, with the output coming from the ASR can contain a lot of numbers, dollars, times, right? And the formatting might not be pretty to look at or even understand. So let's say you have some text which is, I owe him $2,000, and you want to format it so that it's more readable to the user. So there is something known as weighted finite state transducers. Basically, you pass a string along the transducer, and it basically transforms each character based on a set of grammar rules which we have written for each language. And you can actually convert number to words, but much more than that. You can even handle currencies, times, addresses, and whatnot. So all this is open sourced again. There's a library called Indic. You can go and have a look at it. So the next thing I wanted to talk about is domain adaptation and multilingual subtitling, right? So what is domain adaptation? A lot of times you want to use your ASR models in a particular domain, and those words might not be present in training, like in finance domain or in medical domain, a lot of medical terminology, right? So how do you make sure that your ASR models are working fine even there, right? So we developed tools to actually extract keywords from text, because collecting text is easy, right? You can extract keywords from there. You can artificially boost the probabilities of those words while decoding. And you have an ASR model that is domain ready without any human intervention, if you just give it enough text to extract keywords from. The other thing is multilingual subtitling. So Indians are bilingual by nature, right? All of us speak at least 2 languages, if not more. And even when we are speaking to our friends, colleagues, we use 2 to 3 languages, right? So you are building models in monolingual space. You are building ASR models in Hindi, in English. And when you want to transcribe an audio which contains multiple languages, how do you do that? Multilingual models research has been going on, but they are getting better, but they still have a long way to go. They tend to not work so well in noisy environments, right? So how do you do that? So we developed some tricks and techniques to basically do multilingual subtitling as well. You can transcribe text, audio to text using both the models, and then select text based on some intelligent filtering based on language model perplexity. I'll not talk about that in detail, but you can go have a look. So there's a summary. So we have automatic punctuation and text, inverse text normalization in 12 Indic languages, and domain adaptation and multilingual subtitling are actually language agnostic. If you have a pair of languages, you can do it in any language. They're not tied to a particular language rule or model. These are the approaches. So in the end, I just wanted to show a demo. So this is a podcast called Market Mantra. I think this is there by Prasar Bharati on YouTube every week. It contains a lot of domain-specific words related to finance domain, and it has speakers from English, from Hindi, and sometimes some other language if callers call in. So we just have a snippet of it, basically to showcase multilingual subtitling and domain adaptation. So I'll just play it.
Welcome to this Wednesday edition of Market Mantra, the program in which we give you a complete update on the economic, business and stock market news of the day. My name is V. Ravi Kumar, and with me is my co-anchor in Hindi, Sonu Sood.
धन्यवाद रवि। नमस्कार श्रोताओं, मार्केट मंत्र में आपका स्वागत है। रोज की तरह आज भी हम देश और दुनिया से आर्थिक, व्यापारिक और शेयर बाजार के ताजा समाचार आप तक लाएंगे और उन पर चर्चा करेंगे। चर्चा के लिए स्टूडियो में आमंत्रित है वरिष्ठ आर्थिक विशेषज्ञ जयंतो दास। जयंतो नमस्कार, कार्यक्रम में आपका स्वागत है।
शुक्रिया।
और अब हेडलाइंस के साथ हैं वी रवि कुमार।
RBI hikes repo rate by 40 basis points to 4.40%. LIC launches its IPO for general public to remain open till the 9th of this month. Domestic stocks decline more than 2%. Sensex closes below 55,700 mark. Nifty settles below the 16,700 level. And Brent crude prices hover around $109 per barrel mark.
भारतीय रिजर्व बैंक ने रेपो दर में 40 आधार अंकों की बढ़ोतरी कर दी। इसके साथ ही रेपो दर 4.4% हो गई। भारतीय जीवन बीमा निगम
So I think you get the picture. There were a lot of proper nouns as well, if you saw, like we, Rami Kumar, Sono, Sood. So we had adopted our language models for proper nouns as well. And all the numbers were also coming out perfectly, and there were some mistakes, of course. We are still working on it. But yeah. So there's a lot of work which still needs to be done. All these models are fairly heavy. These are around 300 to 350 MB in size. We want to improve the throughput of these models. We want to reduce them so that they can be deployed even without GPUs on multiple edge devices. So this is work which we are still doing. We also wanted to come out with basically ASR models which are streaming architectures by native design. You don't want to do a lot of engineering around streaming. So yeah, we are still working on it. And check out Vakyansh models, Vakyansh papers on GitHub. We have websites also, documentation, and feel free to use it and send us your feedback.